Working on the command line is very efficient, but it needs something to make it more interesting. A Rubik's Cube terminal screensaver. However, I'm going to limit myself to 3 rules. I can only use NeoVim and my own custom Lua config, C++ and a standard library, and everything must be done via a command line interface. I also want this project to be able to run at least 240 FPS, and explain some concepts using mana. To begin, we're going to plot points in 3D space to build a cube and then rotate them around with 3 angles, C, B, and A, which will rotate a point around the X, Y, and Z axes respectively. The problem with this is that some points will overlap when rendering, which is inefficient. Instead of this, we will plot points on the surface of the cube, and before moving on, make sure that our surface normals and light vectors are normalized, which will make our lives easier later on. My first try didn't work as expected, so I tried creating a 2D version to make sure I was drawing to the console correctly. This ended up working despite it glitching. I then decided to create a plane and rotate it in 3D space with the now working render code. This resulted in some inconsistencies in the plane caused by the point spacing spanning the plane, in addition to the debug info being displayed incorrectly. This can be fixed by dynamically setting the spacing based on the terminal width. This ended up solving the problem, so I moved on to adding the rest of the planes of the cube and rendering each of them with a different character to tell them apart. Version 4 of the cube had some performance improvements that made it glitch far less. Moving on, I added a unique color to each face of the cube to complement the black background. This is done by using ANSI escape codes before drawing each character to give its color. However, we are limited to the default terminal color scheme, unless our terminal supports 8-bit or true color. Although it's starting to resemble Rubik's Cube, we still need something to make it more interesting. Lighting. I want to position a light source above and behind the viewer, so that when the cube's faces face the light source, they will light up. We can't just change the brightness of the character due to the previous limitations I mentioned, so instead we will rely on some math and visual tricks. We can do this by taking the surface normal of the cube's faces and calculating the dot product of it and the light source. By normalizing both of these vectors, we are guaranteed that the resulting value will have a range of plus or minus 1. The luminance value will be positive if the vectors are facing the same direction, negative if facing the opposite direction, and 0 if the 2 vectors are perpendicular to each other. We can then map the luminance value to an index range of 0 through 11 by multiplying by 11. This illuminance index maps to a character array, and here's where the brightness solution comes into play. Certain characters take up more space of the pixel, which our eyes can perceive as relative brightness. By using this idea, we can simulate the cube's faces being illuminated by a light source without actually changing the terminal or screen's brightness. So far this is looking nice, but it is still missing what makes a Rubik's Cube. It's individual cubes that can be scrambled. Instead of calculating and rendering each separate cube, I will instead paint black characters where the lines go. This will give off the illusion that we are after without decreasing the performance by much. Applying these changes gives us a result that is looking much more like a Rubik's Cube. However, I think we can still improve performance much and make this a smooth animation. Slowing down each frame allows us to see with much more clarity how each frame is being rendered. I also decided to implement a simple profile to measure frame times. It's averaging 8 to 10 milliseconds per frame, which I'd like to bring down to under 4 milliseconds to reach my goal of rendering at 240 FPS. To improve performance further, let's take a look at how our buffers work to render a frame. We plot points on the surface of the cube, which are then rotated, and their depth are compared to the Z buffer to make sure that we only draw that point if it is in front of another point. This makes sure that we don't draw 2 points in the same position. I am also storing a color buffer of the same length to store that pixel color. Upon initialization, it is set to the reset ANSI code so that when we draw a character, it resets the previous styles and only changes it to a set color if the pixel is added to the Z buffer. Going back to the slowed down example, we can see that some characters don't change color or character from frame to frame. However, they are still being drawn to the console. This is a massive performance opportunity that we can take advantage of. Instead of resetting the buffers at the beginning of each frame, we will instead store the previous buffers into their own buffers and write the current frame to new buffers as we have previously done. I decided to create my buffers at a global scope so that I can allocate memory upon initialization and not have to do so for each frame. Then, when drawing the buffers to the console, we will compare the previous and current frame and only draw the pixels that changed. In addition to this, rendering will be done on the terminal's alternate buffer so that our previous terminal info isn't changed. To further improve performance, I switched from accessing the vector elements with the .add operator to using vector iterators and pointers. With these two changes, frame times got reduced from 8 milliseconds to 2 milliseconds, which is a 400% increase in performance. We're now rendering at 500 FPS, which is way above our original goal of rendering at 240 FPS. As an additional feature, I also resize the buffers when the terminal size changes, to allow for dynamic rendering in real time without having to recompile the code. To get a better understanding of the cube's performance, I decided to override a new operator to count how many memory allocations are done over the lifetime of the program and display some debug info to the console. I also decided that instead of using the standard library string, I switched to using constant char pointers and std string view. I'll link a couple of the channel's videos about string optimizations here, as they are well made and have examples on performance improvements, so make sure to go check them out. With less memory allocations, average frame times were reduced from an average of 2.5 milliseconds down to 250 microseconds, which is a 10 times improvement. We are now easily rendering at an average of 4000 FPS for a 94 by 36 terminal window. However, we can still optimize this further and do more than 4000 FPS.
Stop it. Get some help.
By removing the last .at operators for square brackets, the compiler doesn't check for vector bounds, which saves us a few instructions per frame. Doing so reduces the average frame time by 20 microseconds, which is roughly equivalent to 4500 FPS. Running our screens array at blazingly fast speeds is fun and all. However, I'd like to be able to set a constant FPS limit so that it isn't running at 4,500 FPS all the time. This can be done by measuring the desired frame time from a predetermined FPS value and setting the current thread to sleep until our current time plus the frame time is reached. This allows us to cap the FPS and set it to a smooth 60 FPS for regular use. To wrap up this video, I also decided to improve the profiler to be scope-based and to be able to store frame times in a vector for profiling and debug info. This works by creating a timer class which, upon calling its constructor, stores its current time, and when the current scope ends, the destructor is called, which takes the current time and stores the time difference in the vector. This allows for easy scope-based profiling with a single line of code. This updated profiler was inspired by the Cherno's timing video, which I will also link in the top right hand corner. Furthermore, by using some preprocessor directives, we can disable profiling for the whole program, which is very useful for quick profiling and debugging. Overall, the cube is very efficient. However, it can still be improved to reach 5000 FPS with further optimizations, which I may cover in a future video. Thanks for watching, and I'll see you next time.